All right, good afternoon, everyone. Wanted to take you through our mixed factors ANOVA example. We didn't get a chance to go through in class. Again, this one looking at uh, differences across groups in a series of ordered means. Um, so we're going to be using our worksheet here, the 3x4 repeated measures ANOVA for the ordered means. This is what you should be following along with in terms of handouts. Just as a reminder for these data, what we have are treatment scores for depression at baseline or intake, scores at 2 weeks, at 4 weeks, and 6 weeks at the end of treatment. And so we're following people who are experiencing symptoms of depression, looking for reductions in those symptoms over the course of treatment. And then we've got three different programs. We've got program 1, we've got program 2, and program 3. So with this mixed factors ANOVA, we've got a within subject effect, which is our depression scores. We've got a between subject effect, which is our program. And so our questions that we're addressing within this, the mixed factors ANOVA model here, one, do depression scores mean score vary over the course of 6-week inpatient hospitalization? So are we seeing differences in repeated measures or repeated assessments of depression over time? Two, our question is, do depression scores differ across treatment program? This is our between subject effect. Remember, this would be if we were to collapse all of the depression scores for everybody, take the average across the intervention and see whether or not we have differences in program 1, 2, and 3. That's not a question that's generally as important or relevant, but it is something that we'll get out of this analysis. And then finally, does the pattern of depression scores over assessment differ based on what treatment or what program students are getting? Okay, or not students, so patients. All right, so we're going to be working with our ordered means data set here. We're not going to worry about screening this. The only thing that I will do is take a look and see if we've got missing data. So I'm just sorting here in SPSS. So our depression scores look all good. We're not missing any depression scores, but it looks like we have some missing scores in program. So what I'm going to do, if we were screening this appropriately, we won't do that in this video. We would go through and make a note that we're missing some data here. But what I'm going to do is I'm just going to get rid of all of those, and I'm going to file, save as, just call this scrap. Save that as a scrap file, just so we're not deleting scores that we'll need. Okay, so we've got full data now for each one of our things. Again, we would assume that we'd gone through and screened this at some point, but these data actually aren't looking too bad. And then we got scores for programs 1, 2, and 3. Okay, so first thing we're going to do is we're going to start off with just running our omnibus effects for our mixed factors ANOVA. So we're going to go to Analyze, down to General Linear Model, down to Repeated Measures. Okay, first thing we need to do is identify our within subject effect. And so I'm going to call this assessment, or we'll call this, we'll call this assessment. Okay, and I've got 4 repeated measures here. So I'm going to go hit Add. I'm going to hit Define. Okay, and I want this to be BDI1, BDI2, BDI3, and BDI4, looking at depression scores at baseline, 2 weeks, 4 weeks, and 6 weeks. Okay, and then I'm going to go through and take our program, and that's going to be our between subjects factor. Okay, this is the our difference groups, and this is going to be our between for our interaction here. So we don't have to worry about that. We can go to plots, and I'm going to say, okay, I want program as separate lines, my grouping factor as separate lines, assessment on my horizontal axis. I'm going to hit Add. I don't like SPSS's graphs, but this will just give us something to look at. We're going to hit Continue here. Post-hocs, we don't need to worry about that. Save, we don't worry there. But for options, what I'm going to do is I'm going to ask for descriptive statistics, estimates of effect size, and homogeneity variance tests. Other things we won't really worry about too much here. So I'm going to hit continue. And then what I'm going to do is I'm going to paste this to a syntax file. So I'm going to paste this up. We've got keeping track of the analyses that we're running. So move that right up here. Okay, so this is going to give us our omnibus mixed factors ANOVA model for these data. So I'm going to run it. All right. So if we're looking at output here, I've got my measures, BDI 1, 2, 3, and 4. This is going to be baseline, whoops, come on now, baseline, 2 weeks, 4 weeks, and 6 weeks. We've got 141 people in program 1, 101 people in program 2, 123 in program 3. These are descriptive statistics. We'll come back to these in a moment. But this is just looking at for each group across each assessment means, and then overall means at each time point. Boxes test, we can ignore that. Multivariate tests, we can ignore that, as we discussed in class. Test of sphericity, we already assume that we're gonna violate that sphericity assumption, so we don't even need to worry about that too much. And what we can do is we can go right down into our test of within subjects effects. Okay, so if we're looking here, we see again we're going to interpret this greenhouse geyser corrected F's here, but we can see that we have in these data very strong evidence that our measures of or average depression score over the course of treatment is, we have a lot of evidence that that's not the same, right? So we have a strong within subject effect going on right here. Again, this is just saying, testing the null hypothesis that the mean at time 1 is equal to the mean at time 2 is equal to the mean at time 3. We see that that's absolutely not the case, and so we've got an effect there. But as we go down through and we take a look, we also see we have an interaction here. Okay, this interaction, this is, remember, program is our between subjects factor, assessment is our within subjects factor, and we have an interaction. So we have a between by within interaction here. And what this is saying is it's saying that the pattern of means across repeated assessments differ based on what treatment program patients are in. Okay, so we've got essentially a moderation effect. This main effect here of our repeated assessment no longer a main effect, it's a conditional effect, because the specific pattern of means over the course of depression means over the course of treatment are going to be determined specifically by what program participants are in. We see we have a p-value of 0.004 there. What we would want to do for our class is calculate a Bayes factor and an S value for that. And so if you pull up, we got our handy dandy calculator here. Calculate an S value and a Bayes factor. I go through and I double click and capture that. Okay, so this is going to give me an S value of 8, right? Suggesting that for these data evidence against the null hypotheses of that the pattern of means over the course of treatment is going to be identical for each one of the treatment groups. Evidence against that null hypothesis would be equivalent to getting 8 consecutive head flips on a hypothesized fair coin. So we've got starting to be some fairly strong evidence or fairly convincing evidence against the null hypotheses. Our Bayes factor here, 16.03, indicating that at most, in a perfect world, these data would suggest that our alternative hypotheses of a moderating effective program on repeated assessment of BDI score, we're seeing the odds of that alternative hypothesis being about 16 times that of the null hypothesis. And so some good evidence here, but then we're just using our calculator for that. So going back to our output, So we've got a between by within interaction, our test of within subjects contrasts. We're going to ignore that for right now. If we go down to see our Levine's test, this is telling us whether or not we have differences in, or whether or not we're seeing differences in, differences in the population variability of depression scores across individual groups at intake or baseline and week 2. We're not seeing violations of homogeneity variance, but we are seeing that across programs we're seeing evidence of differences in the variability of scores across these programs at both week 4 and at week 6. So we're going to tuck that in the back of our head and say that might be something that we want to take about and consider later as we move forward. Okay, and then our test of between subjects effects. Again, this is just going to be a test of whether or not collapsing across repeated measures. If we were to take the average of each group at baseline, week 2, week 4, and week 6, and compare that average across those measures for groups 1, 2, and 3, looks like we're not seeing strong evidence of systematic differences there. But again, that tested between subjects effects is not something we many times are interested in, but just kind of wanting to know what's going on with your data here. So if we go down and take a look at our estimate of our marginal mean, or estimate of our means here, what we're seeing is kind of everybody's reducing or decreasing here, but we're seeing that maybe we see some differences here, maybe we see some differences here. Not super sure quite yet what we have going on. Anytime you have an interaction effect, my first recommendation would be go through and plot that out. Now, SPSS has given us a plot here. I don't really care for those plots all that much. What I'm going to do, or I did, is go back up and go to our descriptives and take a look and just plot these out in Excel. Just like these plots a little bit better. And we can see if we go through and create a table where we've got the mean for program 1 at baseline 2 weeks, 4 weeks, 6 weeks, 2 weeks, 4 weeks, and 6 weeks. So 2 weeks, 4 weeks, or baseline 2 weeks, 4 weeks, 6 weeks, and the same thing for program 2 and program 3 here. We're seeing that we're getting, again, just a little bit nicer graph of what may be going on. Okay, so here we've got our effect. We've plotted it out. What we need to do now is think about what we're going to do with this, right? So if we go through and we make an interpretation of our omnibus effect here, we might say that the evaluation of our 3x4 mixed factor ANOVA with our repeated measures on the final factor giving us fairly strong support for a group by session interaction. Here's our p-value, our s-value, our Bayes factor. Results suggest that reductions in depression over the course of intervention differs across treatment groups. Okay, so here's our graph. Now what we want to do is figure out how are we going to go through and start to, what's our approach going to be to teasing out what this interaction is, what's going on in this interaction. Now, if we've committed these people or these patients into treatment, we're assuming that all of these treatments are going to be effective, right? And so one thing we might want to do is go through and see from baseline, from where people start to 6 weeks where they end, pre to post, looking at within subject change within each treatment group, okay? And the question here is, are we seeing, do we have evidence of greater reductions in one group versus another group? We can treat these as a priori, and we can say, okay, we expect people to improve for each one of these. And so what we're going to do is we're going to calculate confidence intervals, effect sizes for each of these treatment groups to see the magnitude of change from beginning to end. Okay. Now there's a lot of other pairwise tests that we could do with this. I could look at one for within each group. I could look at one baseline versus 2 weeks, baseline versus 4, 2 versus 4, 4 versus 6. But as we talked about in class, that's probably not a use. I mean, we could do those, but unless I have a strong reason to go through and test that out, it's probably less relevant than being interested in where people start and where they end within each one of these groups. Okay, so we can say that those are a priori. We had anticipated that we would see reductions. We're just wanting to gauge the magnitude of that. But we also might be interested in a couple of different things. One, do we see that these means for each one of our groups that people didn't start in exactly the same place? I don't know that I'm super confident that these are going to be different, but that could be a question, right? If we see differences in each one of these groups, a question might be whether or not they started all in the same place, or if we started in systematically different points. So we might want to also, as we're doing follow-ups, taking a look to see, were people functionally similar at baseline, right? Also, we might be interested in seeing if people were functionally similar by the time we finished up with treatment here at the end, okay? So here, we're looking at two sets of between subjects tests or contrasts, a total of 6, where we have 1, 2, 3, 4, 5, 6, right? And so what we could do is conceptualize this as 6 exploratory tests. So in terms of thinking about how we're going to go through and start probing this between by within interaction, what we could do is we could say, well, we're going to calculate within subject effects from baseline to 6 weeks for each group. So that's going to be 3, we'll call these a priori contrasts or tests to look at the magnitude of reductions over the course of treatment. Okay, but then what we've got is we're going to go through and we're going to examine differences at baseline and at 6 weeks across different treatment programs. Okay, so we've got 6 different contrasts, 3 here, 3 here. These are exploratory, and so what we want to do is we want to make some sort of adjustment. Now, there's a number of different things that we could do, but for this, I like a Benjamini-Hotchberg procedure to go through and adjust for multiple comparisons. So this is going to be our approach to teasing apart and gaining some information on what's going on in this interaction. Okay. Lots of other ways to do it. There's an infinite number of combinations, well, not infinite, but many different ways we could go about this, but this is maybe something that makes a little bit of theoretical, practical sense, and so this is the approach we'll take in this example. Okay, so let's go back to our data. Our first thing we want to do is we want to look at within subjects effects from baseline to 6 weeks within each treatment. Okay. So what we're going to do is we're going to go through to transform, or data, excuse me. We're going to go to split file, and we're going to look at organized groups by program. Okay, so what this is going to do, when we go through and hit paste, I pull up my syntax file here. What this is going to give me is for anything that I do with this split file on, it's going to go through and run it separately within each program. Okay, so I'm going to do that, and then I'm going to go up to Analyze, Compare Means, Paired Sample t-test. Okay, and what I'm going to do is I'm going to look at BDI at 6 weeks minus BDI at intake. I'm putting in 6 weeks first, subtracting where they end up from where they started. That way the sign tells me if they've increased, decreased. I already know because I looked at the graph, but just make it a little bit intuitive here. And I'm going to go through and I'm going to hit paste. So if I'm looking at my syntax file, what we're going to do here is I am going to split the file by program and then look at pre to post change within each one of these individual groups. Okay. So I'm going to run this and then we'll take a look. Okay. So what we've got is we've got program 1 and looking at pre to post treatment change for program 1, for program 2, and for program 3. Okay, so we've got 3 within subjects effects here that we're looking at, and honestly, I'm really not concerned, and we talked about this before in class, I'm really not super concerned about the actual significance test. based on these reductions. These are very clearly with hundreds of people within each one of these. What do we got? We got 141 in group 1, 100 in group 2, 123 in group 3. There's no concern about whether or not that's going to be a difference that's different than 0. So I'm less concerned about the significance test, and maybe I'm more concerned with gauging the magnitude. How much of a difference, how much of a reduction are we seeing within each one of these within each one of these treatment groups? So what I'm going to do, and because SPSS will not do this for you, we have to do a little bit of hand calculations on our own. So if I go through and take a look here, what I'm going to do is I am going to, for each one of these groups, what I'm interested in is documenting the confidence interval, right, for the mean effect. So for program 1, our mean reduction for program 1 is a reduction of 15.38 points on the BDI. That's pretty strong. That's a big reduction, right? But this is my best guess, right? So my best guess for any group of individuals going through program 1, I would expect an average reduction of about 15.38. But I know that's not going to be my true population effect. What I'm going to do is calculate my confidence bounds to look at upper and lower limits of the raw decrease in BDI. And so this confidence interval is saying that my data support estimates of population effects running anywhere from a 13.3, 13.4 point reduction on the BDI to anywhere as high as a 17.4 unit reduction in the BDI. Okay, so here we're seeing clear evidence of reductions. And so in my going to document over program 1, looking at the point reduction, estimated point reduction for this program, and my confidence interval. I got rid of the negatives. Those are sort of semi-arbitrary. But what I'm saying is we're seeing reductions of about a little over 15 points, with a lower end of 13, a little over 13, higher end of about 17. Okay. Then what we're going to do is we're going to calculate an effect size. Now, I might be interested in calculating, so we've got a within subjects effect. And so what I might be interested in doing is calculating a confidence interval around that standardized effect. And if I want to calculate a confidence interval around my Cohen's d, what I need to be using in terms of my standardizer is going to be the standard deviation of the difference score. Now, for these data, running like a Glasses delta, where I would take the mean difference and divide it by the standard deviation at intake, or the standard deviation at baseline, that would actually give me a really nice interpretable effect. But if I do that, remember that I can't run a confidence interval around that. So, but what I do for this example, I do want to calculate a confidence interval around my paired sample D. And so what I'm going to do is I'm going to take the difference between pre-post, and I'm going to divide that by the standard deviation of the difference score. Okay. So if I do this, I'm going to get an effect size estimate of 1.27, suggesting that we're seeing about a little over 1.25 standard deviation reduction in symptoms from intake or from baseline to end of treatment. Okay, that's big. That's a big effect. Now, what I might want to do though is I might want to calculate a confidence interval around this. Remember that to calculate a confidence interval, what we need to do is we need to take this t-value, and we can go through and get a non-centrality parameter for the upper and lower limit of the non-centrality parameter, given this t in the degrees of freedom. And then what we can do is we can use that non-centrality parameter to back translate that into an upper lower limit for d. So here, what we're going to do, if we go to, let's see, pull up my handy Steiger calculator here. And if I, punch in, so I'm looking at a 95% confidence interval for t. My t value is 15.116. My degrees of freedom for this test are 140. I compute that, and I get a lower bound for my non-centrality parameter of 12.460, an upper of 17.741, call it. Okay, so I can take those, record those here, right? And so I take, to get the upper and lower limit of from my non-centrality parameter, I'm going to take my limit and divide it by, for the paired sample test, I'm going to divide it by the square root of my sample size. Do the same thing for my upper limit. Take that, divide that by the square root of my sample size. And what this is going to give me is it's going to give me confidence bounds around my effect here. Okay. So in this example, what we've done is we've gone through, we know that reductions from pre to post, we know that's going to be not different than 0. So the hypotheses test is not terribly useful. But what we do want to do is take a look at the magnitude of change. And what we're seeing is our best guess for expected reductions in symptoms for people completing program 1 is going to be a little over 15 points, with a lower bound in the population of 13.4, an upper bound of 17.4. So again, some pretty impressive gains. My standardized effect, D1, about D of 1.27. Again, looking at sort of over a 1.25 standard deviation reduction, and the confidence interval on that effect size, based on we've got a pretty good size sample. Even the lower bound of that confidence interval is suggesting over a full standard deviation reduction in symptoms, even as my most conservative estimate. So these data support as low an effect size as 1.05 with a high of about 1.5. So my confidence bound here saying these data support anything from about a 1 to a 1.5 standard deviation reduction in symptoms for program 1 alone. Okay, so we can go through and run that, make sure that we've documented that outcome, but then want to do the same thing functionally for program 2 and program 3. So for program 2, we see our point estimate of our reduction. So for program 2, we've got about 19.3 unit reduction, with population estimates ranging from 16.7 to 21.9. If we go through, calculate our within subjects D, take my mean of my difference scores here, or the difference in time 1 and time 2, divided by the standard deviation of change, gives me a point estimate of my effect size of 1.46, about 1.5. So we're saying that our best guess based on these data is that we're expecting people to have a 1.5 unit standard, 1.5 standard deviation change in depression symptoms in program 2 from baseline to finish, pre to post. And then once again, if we go through, pop up our Steiger calculator, t-value is 14.749 with 100 degrees of freedom. Run that, gives us upper and lower limits of our non-centrality parameter. We can back translate that into upper and lower limits for D, giving me lower limit supported by the data on my effect size of about 1.2, an upper limit of about 1.8, or 1 3/4 standard. As much, these data support population effects as large as 1 3/4 standard deviation reduction in symptoms, which is really massive. Okay, same thing if we go down to program 3. We see here over a 20-point reduction. If we take our pre-post difference divided by our standard deviation of the difference scores, gives me an effect size of close to over 1.5, 1.66. If I go through and run again, same thing, non-centrality parameter, get my upper and lower limits on my non-centrality parameters, back translate those into upper and lower limit for my D, I get anything from a 1.39 standard deviation reduction from pre to post, all the way up to almost a 2 standard deviation reduction in BDI scores from pre to post. This is really, really impressive, right? So at the low end, so the minimum plausible value for D supported by these data for the true population effect is something that's close to 1.4 standard deviation reduction. So this is very, very large, okay? But remember that our interaction effect, right, says that we're seeing that program has an impact on the pattern of means over the course of intervention, right? So our question probably should be, is this what we're seeing? Is this contributing? Are differences from pre to post contributing to this interaction? Well, so we've got means, we've got standard deviation, or we've got point estimates, we've got effect sizes, but this can be kind of hard to kind of all put together in terms of trying to see what this is actually looking like. A visualization is often nice. And so one thing that I've started to do that I like quite a bit, you can find this, Geoff Cumming has an ESCI tool, basically a spreadsheet where I can plug in values, upper and lower limits, right? And what it's going to do is it's going to give me a plot for effect sizes or confidence intervals, whatever I want to do. And so if I take these values and I plug these into my calculator here, I get something like this. So here, I just kind of put them in the middle. So we've got program, this is program 1, program 2, and program 3. These are our point estimates for our and confidence intervals around our mean difference. Here's point estimates and confidence intervals around effect size D, right? So what we're seeing, and we can see this in our numbers, but this is just a nice way to visualize it. We're seeing in terms of raw reduction in points on average in program 1, 2, and 3. We're seeing sort of clear evidence, or pretty strong evidence, that we're seeing greater reductions in program 3 relative to program 1, and then program 2 and 3 look fairly similar. A little more overlap between program 1 and 2 here, but looking like potentially seeing greater effects for programs 2 and 3 relative to program 1. Our effect size estimates and correlation and confidence intervals around D a little less conclusive, but we're seeing kind of a increase in standardized effect across program 1, program 2, program 3. Possible in terms of similar here that we're seeing systematically larger effect sizes for program 3 relative to program 1, with program 2 right here in the middle. So we've run our numbers, but we need to be thinking about, what does this all mean? Well, we might hypothesize, based on our evaluation of within subjects effects across individual programs, that we may have some sort of potential for an enhanced response in program 2 and 3 relative to program 1, right? And so this is something that could definitely be contributing to that interaction effect, in that the pattern of means, or the pattern of reduction from baseline to 6 weeks, is different for program 1, 2, and 3. Okay, so this gives us a sense for what's going on potentially with our within subjects effect. But recall that we also wanted to go through and take a look at differences between, right? And so the question here at baseline is there evidence that our patients are starting out at a systematically different place, right? Maybe program 3 is working better just because those are the people who had started out the worst or started out the sort of the best, right? And then also taking a look maybe at 6 weeks to say, are we seeing systematic differences? Are we seeing lower levels of symptoms at 6 weeks at the end of treatment across groups, right? Now we're going to call these exploratory, and we're going to go through and look at pairwise. 1, 2, 3 differences here. 1, 2, 3 differences here. And recall that we're going to address this or control for this with a Benjamini-Hotchberg. Okay. So going back to our data, what we're wanting to do is we want to go through, and I could go to Analyze, Split File, and I could hit Analyze All Cases. I could paste that, right? And if I hit that, that's going to turn my split file off. In SPSS, I can also just sort something, and that's going to turn that off as well. But in terms of remembering what you've got going on in your data file, or in your syntax file, it's nice to have that split file off. And now what we're going to do is we're going to look for and ask SPSS to give us between subjects comparisons across group at baseline, and at 6 weeks. Okay, so what I'm going to do is I'm going to go back and I'm going to analyze. I'm going to go to compare means, and I'm going to go independent sample t-test, and I'm interested in looking at differences at intake and at 6 weeks, and I'm going to look at differences across program. Now I'm going to have to define groups, so I'm going to say I'm going to compare groups 1 and 2 for this one. I'm going to hit continue. Yeah, nothing that we need there, and I'm going to go ahead and hit paste. Okay, so if I go to my syntax file here, what I've got is a test in SPSS compare programs 1 and 2. Now I could go back through the pull down menu, but that would be a pain. So I'm just going to go through and change this and say, okay, I'm going to do the same thing. Compare programs 1 and 3. And compare programs 2 and 3. Okay, so I'm going to compare programs 1 and 2 at baseline in 6 weeks. 1 and 3 baseline in 6 weeks. 2 and 3 baseline in 6 weeks. Okay. We go through, run this. All right. So what we've got is we've got our independent sample t-test looking at differences across our groups, 1 and 2, 1 and 3, 2 and 3, both at intake in 6 weeks. So we've run a lot of tests here. Just going down through, we can see something that would register as per comparison rates here at intake. We're seeing that we don't have our Levine's test telling us we don't have strong evidence of a violation of homogeneity of variance. So it looks like we've got a test statistic between looking at groups 1 and 2 at intake or at baseline. We're seeing a test statistic of 2.39, p-value of 0.017. Looks like we're not seeing differences at 1 and 2 at the end of treatment at 6 weeks. Here, we're seeing comparing groups 1 and 3. Doesn't look like there's much going on at baseline, but here we've got a violation of homogeneity of variance, so we're going to go down to equal variance is not assumed, and we're seeing we've got a test statistic of 2.72, a p-value 0.007, so looking like potential differences, maybe evidence of potential differences at end of treatment between 1 and 3, and then same thing comparing groups 2 and 3. Nothing much going on, looks like at baseline, but at 6 weeks we're seeing again violation of homogeneity of variance. We're down here seeing that we've got a test statistic of 2.387, p-value 0.018, suggesting possible differences there at the end of treatment. Okay, so we've got 1, 2, 3, 4, 5, 6 different tests, right? And so remember, with Benjamini-Hotchberg, we don't want to jump in and start making strong interpretations quite yet. What we're going to do is we're going to run these through Benjamini-Hotchberg procedure. And so what I'm going to do is I'm going to, in Excel, I'm going to go through and starting with my first one, I'm going to start recording in this table. I've got my baseline 1 versus 2, 6 weeks 1 versus 2, entering my p-value, and my test statistic, my p-value, test statistic and p-value for this first contrast, right? I'm going to go down here, do the same thing, 1.38 for 0.168 in terms of p-value. Here I've got a violation of homogeneity of variance, so I drop this down. I'm looking at this value here, 2.732, 0.70. Okay, got p-value at 6 weeks, and then the same thing down here. And then in this table, what I've done is calculate S values, Bayes factor, and confidence intervals around G and around sort of my point estimate and effect in my G for cases or for tests that meet traditional or conventional benchmarks for interpretation. Looks like I forgot one there for that first baseline test, so we can go through and add that in. So I'm going to go through and let's see. My first one. Yep, my first one. All right, so my test statistic here is going to be, so I've got to get this up so I can see what's happening here. Oops, it's not helpful. Okay, here we go. So my mean difference is 3.991. My confidence bound for this is going to be 0.705, 7.277. Okay. I'm going to calculate an S value here. Oops. I'm going to go grab my p-value, take this over to my S value calculator, drop that in there. It's going to give me an S value for this of 6 and a Bayes factor of 5.20. Round that out. And then what I want to do is I want to go through and I want to calculate my effect size here. So again, what I'm going to do is I'm going to pull up handy dandy calculator that we've built in class and go up to my, go up to my there we go. All right, so my mean for my first group, 24.7. Mean for my second group, 28.69. Standard deviation, 12.586. 13.083. And I've got 141 people in the first group, 101 in group 2. Okay. And then what I'm going to do is I'm going to go through and calculate non-centrality parameters. So if I go and I say my test statistic 2.393, my degrees of freedom for this test 240, compute that. All right, and so this is going to give me lower limit of 0.419, upper limit of my non-centrality 4.362. All right, and so now what I can do is automated all this so that I can go through and pop it into my thing. So what we're going to do is we're going to call this my G is 0.312, we'll call it, and the confidence bounds around this are going to be 0.055 and 0.569. Okay, so what we've done here is just go through, put in means, standard deviation, sample sizes, upper and lower limit for our confidence bound. I'm looking at here my G. This is using my effect size with my pooled standard error, or excuse me, my pooled standard deviation, and then going to go look at my upper and lower based on my calculator here. Okay, so get rid of that, and so what we've got now is my Benjamini-Hotchberg table, where I've got all of my comparisons. I've gotten in some additional statistics for things that might come up as relevant. What I'm going to do, I'm actually going to delete this for right now, and what I'm going to go through, I'm going to insert a variable call this index. And what I'm going to do is I'm going to, well, wait, before I do that, this data, I'm going to go view, freeze that top pane. So that's not go through and do stuff. Okay. So what I want to do is I want to go through, these are all my comparisons that I put together. I'm going to go through and sort these by my p-value. And what I'm going to do is I'm going to sort these from largest to smallest. Yep, I want to go through and make sure everything switches over. Okay. And so what I've got is from my test that gives least evidence against the null hypotheses all the way up to my test that gives the most evidence against the null. Okay. So what I'm going to do is I'm going to insert a new variable. I'm going to call index. I'm going to go 6, 5, 4, 3, 2, 1. Okay. So we've now labeled these in order from least evidence to strongest evidence. And what I'm going to do now is I'm going to enter insert a variable for my Benjamini-Hotchberg. Okay. And remember that Benjamini-Hotchberg criterion is going to be equal to my index divided by the number of the number of tests that I've run. So I've got 6 here, multiplied by my alpha level, 0.05. Okay. So my significance level for my criteria for my first test with the least evidence is 0.05. But then what I'm going to do is I can go down through and run this down. And what it's going to do is it's going to give me 5 divided by 6 times 0.05, 4 divided by 6, 3. And so what we can see is that our criteria for statistical significance is increasing. You know, our false, and so this is giving us a control over false discovery rate with a Benjamini-Hotchberg. And what we're going to do is we're going to choose tests for interpretation that exceed our threshold. Now it looks like we got a tie here. Let's go for, okay. So what we've got when we go through and take a look is it looks like we've got one test here at the endpoint that is less than our criterion variable here. This one doesn't look like it quite cuts the mustard, but then again another endpoint we're seeing here, right? So what we've got is we've got 2 tests, both at the end of treatment. We've got 2 versus 3 and 1 versus 3. And if we take a look back at our graph, so this is group 1 and group 2, both of these finding sort of evidence even with the more stringent tests that yes, these 2 groups, was it 1 and 2, look to be different than program 3 here at the end. Okay, so we can go down through and take a look at our stuff here. We go down and paste this table in. This is where we got our Benjamini-Hotchberg here, and we've highlighted the fact that the 2 tests that are giving us the most confidence that we have in fact we do have evidence of something even under more stringent control are the difference between program 2 and 3 at 6 weeks and 1 at 3 at 6 weeks. And this is important because again, both of these tests are corresponding to differences at where people finish up. Okay. Now, if we go through and we take a look at confidence intervals around our point estimate of our effect in our G, remember that we've got a lot of people in this sample. Okay. So when we actually look at at the end of treatment, it looks like group 3 is about 3 points lower on the BDI than group 2, and again about 3 points lower, a little under 3 points lower than group 1 on the BDI at the end of treatment. If you're a clinical psychologist and you've worked with a BDI, I'm not that concerned about or too worked up about a 3-point difference on the BDI, right? And if we look at our lower bounds for our confidence intervals, we're seeing that difference, our data would support a population difference between 2 and 3 of a 0.5 point at between 1 and 3, about less than a point. Upper bound could be as high as 5 points for both groups, and that's fairly impressive, or I mean, maybe not impressive, but it's at least something. But the lower bound suggesting that, boy, we don't know really if there's we don't have strong evidence that that might be a meaningful effect. So we're keeping that in the back of our mind. Same thing in looking at our effect size for both of these, both 2 versus 3 and 1 versus 3, about a third of a standard deviation reduction based on our data that we've collected here. But again, lower bound for both of these, suggesting that our point estimate of our effect, our data would support anything as low as about a tenth of a standard deviation difference. So in the grand scheme of things, I'm probably more impressed with the within subjects effects than the between subjects effects, but that's not surprising because the within subjects effects are much, much more impressive. So as we go down through, if we were to tie all this together, so we went through and we ran some within subjects contrasts and between subjects contrasts. If we were to write this up for class, and again, these are in your lecture slides, this is how we might put some of this stuff together, right? We're saying that we're seeing large clinically significant reductions for all 3 programs, 1, 2, and 3, right? We're looking at some potential advantage for enhanced treatment response in program 2 and 3 relative to changes in program 1. Specifically in program 3, we're seeing over average reduction of over 20 points, point estimates ranging, with population estimates ranging from about 18 points to over 22 points. Program 1, only about a 15-point reduction in unobserved data, with population estimates from 13.4 to 17.4. Reductions in program 2 similar to program 1. Okay, so we're seeing within our within subjects effects a potential advantage of program 3. But for all 3 of these programs, these are all very, very effective in terms of reducing depression, at least based on the data that we've collected here. Okay. Then we went to some exploratory analyses, looking at differences both at intake or baseline in 6 weeks. Some evidence of potentially greater responding in group 3. Not a lot of support for differences in initial depression. Okay, although we did see one of those contrasts popping up, but didn't meet the threshold for interpretation with our correction. But at 6 weeks, we did see some evidence of lower symptoms in at the conclusion of treatment in program 3 relative to program 1 and 2. But the magnitude of reduction or the magnitude of improvement, at least on a between subjects factor, maybe less impressive here. So, but when we're looking at focusing primarily on our within subjects tests, looking like we're seeing some evidence of a stronger reduction within program 2 and 3. So this is just kind of going through, talking about what's going on, and then kind of pulling it all together. Overall results offer preliminary support for differences within subjects effects indicating greater reductions in program 3 and 2 relative to 1. So some incremental benefit for our between subjects contrast. So again, together thinking about it, this is having greatest support for reductions in or enhanced response in 3 relative to program 1, but somewhat less compelling for 2. So we're just trying to pull all this together. We've gone through, ran a lot of stuff, just wanted to make sure that we're tying it all together in a way that makes some sense. Okay, so that takes us through our example. Again, all of this is laid out here in the handout that you got in class. A couple little bells, extra little bells and whistles, but again, for the hand calculations, all those are laid out here so you can follow along and take a look at that. So hope this was helpful. Let me know if you have any questions, and good luck with these.